let's get started. Hi, folks. My name is Casey James, and I'm the resident meter engineer here at GridSME. I've been working in metering in the CalISO market for about 7 years now. I've spent the first 3 of those mostly out in the field, and the rest mostly behind a desk. Today, I'm going to talk about the fundamentals of what makes the market, what the market is seeing currently without getting too into the weeds. I know there's going to be a few specialists listening in today, so I want to acknowledge that everything I say today is full of caveats, exceptions, and special cases. Please forgive the generalities. Further, I'm omitting information about auxiliary loads and avoiding utility idiosyncrasies. This presentation is guided at the sweeping overview of why metering is the way that it is in the CalISO. I'm going to start off slow and then ramp up into the more complex stuff. It's going to feel a little bit like a physics course where you go from bored to confused in the blink of an eye. I would love to answer questions in throughout, but we've got a rather big group here today, so if we could save those for the end, we'll just chug this train right along. Just to give everyone a rundown of what we're going to hit today, the top of this is going to be metering basics and loss compensation. We'll go over a couple of methods acceptable for CalISO metered entities. And at a point, we'll need to discuss the difference between CalISO metered entities and scheduling coordinated metered entities, because we can only do some types of metering schemes as an SCME. Finally, we can finish with some more advanced methodologies. So why does metering matter? Well, metering matters because a meter is considered one of the best sources of truth for a plant or a load. And being a source of trustworthy data is an important egg. It's so trustworthy, in fact, that people agree to buy and sell whatever it measures. In the CalISO market and many others, there are high standards on the quality of reporting. Meter devices are tested repeatedly. Meter instrumentation is tested repeatedly. Associated meter hardware is tested repeatedly. There are certified inspectors, ANSI standards, in schools about meters. Because at the end of the day, the accuracy of the meter measurement translates into real dollars. As is often said, the meter is the cash register of a plant. There are many different resources that one may be interested in connecting to the grid. For the purpose of this discussion, we'll regard all fuel types as the same. A meter really can't tell anyway. On the way to getting energy to the grid, there's an agreed point of interconnection. I'll say POI going forward. Now, before we hit the grid, the POI is the only reasonable place we can measure and effectively say, this is the energy making it out of the power plant. So the POI then becomes the place that the CalISO will want to pay a generator from. Okay, so very briefly, we're going to talk about losses. There are 2 main causes for power loss. They are transmission and transformer. A simple way to think about power loss may be soccer. Imagine you kick a ball. The ball rolls along the grass, and as it does, it slows down. If we measure that ball's power at different points along its path, we will have less and less as it goes further down the field. Transmission of power is similar. After miles of transmission over some lines, there's notably less power at a receiving end. We call that missing power loss, and we'll signify it here with a resistor symbol. The zigzags of the symbol are actually supposed to represent electrons bouncing around on a line, thereby slowing down the flow. Physicists will hate that description, but it's too late to fix it now, so we're stuck. I won't get too much into how this transformer works, except to say that it's a ton of wire wrapped around each side of a magnetized core, where the core is this square ring. If you unravel all of the wire and make it a straight length, by golly, it works a lot like a transmission line. The power has to travel the full distance of that wire, and again, we get losses. The core has losses too, but I can't explain that with soccer, so we'll skip over it. And even still, there are more complexities of a transformer. which may better be explained with hockey or cricket, to which I don't know the rules of. In any case, this is the symbol for a transformer. The wiggles on either side are representative of the aforementioned windings. For the rest of the presentation, we're only going to use these symbols off to the right. So if you remember zigzags and squiggles, then we're going to be in good shape. This layout is basically the same as the other, but more graphically similar to a single line diagram. This is a common simplified look at, let's say, a solar plant from the perspective of metering. Here we have the resource and how it connects to the POI. As for the grid, we don't really need to think about what happens above the POI because the POI is where we focus our financial stake. In this example, we are happy that the point of metering is permissible at the POI because the energy measured is the energy that the CALISO will settle at. And we'll just skip over what the utility does. Truth is, though, is that we're not often allowed to meter at the POI. Commonly, a resource might be a little ways away from the POI, and there might be a transformer that steps up the voltage before the POI. This is not at all unusual. The line distance and the transformer will create losses, which means that the power at the POI is less than what was measured at the resource substation. Rest assured, the CALISO will still want the measurement to look as if the generator was at the POI. And for that, we're going to do a little arithmetic. We'll start with a simple formula. Power at the POI equals power gross minus power loss. Now, the power loss is comprised of the transformer and the line loss, but those formulae are just a little too hairy for this setting, so we'll keep it as it is. Now, it's an older term, but it's always helped me visualize what we're trying to accomplish. It's called phantom metering. We pretend that the meter is up here at the POI so that we can clearly see the differences between where we're actually measuring and where we're trying to measure. To resolve this, we can go into the meter, the real meter, and change some of the settings that apply what we call compensation. There's no magic to how this compensation is calculated and put into a meter, but it is generally regarded as very boring, so I won't get too specific here. It will make the meter, the real meter, appear as if we were measuring at the POI. For this example, we have a hybrid resource. Now, a hybrid resource is any single resource with mixed fuel types. It could be solar and battery, solar and wind, wind, coal, and nuclear. It really doesn't matter. If the mixed fuel types report as a single resource, they are considered hybrid. Now, what's shown here is a mixture of PV and battery as fuel types. And in this example, we'll suppose that this is registered as a single hybrid resource. The energy sold to the CALISO is not metered any differently than our previous example of a single fuel type. Again, we'll make the meter appear as if it is at the POI by applying compensation in the meter, but for the purposes of revenue, we don't need to do anything else differently. Now, I'll omit some details here about variable energy resource component metering and another note about renewable energy credit calculations. If anybody is interested in those topics, we can dive in a little bit later. For this example, two separate PV resources are connecting to the same POI. For an ISOME project, it is required that each resource have its own meter. And since it is two resources sharing one interconnection, these resources are considered co-located. Again, we'll want to make the resource look like it's at the POI. But now we have to make sure the losses are split between each resource. We have a calculative method to get the compensation very close. Under normal operating conditions, we can expect that each resource is going to be operating proportionally to the other, since they are both the same fuel type. Consider that at the co-located solar plant, it'll be dark at the same time, cloudy at the same time, and sunny at the same time. So we can expect a similar proportional output. Error rates in this calculative method are generally so small that they are undetectable. You may have noticed that I said individual meters are required for an ISO-ME project. That requirement is not necessarily true for an SCME project. We'll cover more of that later. It isn't too uncommon now for a battery and a PV to enter onto the CalISO market as separate resources at the same site. But this presents a much more complicated scenario. Each meter will have no idea what the other one is measuring, and their resource dispatches are going to be different than each other in a manner that a single point of feeder information is not going to be enough to determine line and transformer losses are going to be. Consider that the PV meter is just one measurement point. It's not measuring the whole line, it's only measuring the PV component. Without having special programming, there's no way to even estimate what the battery meter is measuring. Further, with a battery involved, there are net zero conditions where there are no losses at all. And an average isn't going to be reasonable either, because losses function on an exponential scale. We can no longer reasonably use phantom metering as a method, but we must still compensate to the POI. We can still do standalone metering like this as an ISO-ME project, but the CalISO only requires that we set the losses to their worst case scenario calculation. Not great, and here's why. We're just gonna gently dip our toes into the nerdy for a moment, if you feel like you haven't already. Exhibit A. Let's say that solar and BESS are the same size of 10 megawatts and that our POI limit is 20 megawatts. And in this scenario, only solar is dispatched, producing and putting power onto the grid. The solar meter has no idea what the BESS meter is doing. As a worst case scenario, we should assume that the battery is discharging at a maximum. We would then need to maximize solar and BESS losses. Now, ignore the numbers here because this is more about the principles of mathematics. Here's our maximum loss if only a solar is producing at a maximum. And here's if both are exporting at a maximum. Our total losses quadruples, and our solar resources losses responsibility has unduly doubled. Without shared information between the meters, a worst case assumption can inflict some economic loss because of the calculative assumptions. Exhibit B, solar is producing at full. And again, the solar meter has no idea what the BESS meter is measuring. As a worst case scenario, we assume again that the battery is discharging at a maximum, even though zero power is actually making it to the POI. Solar losses are again needlessly overstated based on the assumption of worst case, but it's even worse. No power is transmitting through the line, nor the transformer, therefore real losses are effectively zero. On top of that, the BESS meter, as a worst case scenario, assumes that it is charging from the grid and is also incurring losses proportional to its 10 megawatts. So both resources are unduly responsible for losses that don't even exist. So how do we solve this? We need the meters to be able to share information with each other so that we can compute losses accurately. Well, in an ISO-ME scheme, we aren't strictly limited to standalone metering. I've rearranged a couple things here to present a common layout, but the principles are the same. We can have meters talk to each other through an intermediary called a calculating meter. Anytime we have a system of meters that talk to each other, we call that a peer-to-peer scheme. Now, this calculating meter is better positioned to know what is happening at the POI. even if it isn't physically at the POI. This meter can measure the sum activity for the resources. Additionally, it is allowed to have direct communication with the PV and BESS meters and know what their individual measurements are. Using these pieces of information, we can perfectly compensate the PV and BESS meters no matter what their behaviors are. If the calculating meter is open source programmable meter, we can have that compensation applied directly to the resource meters. All you need to do is buy an extra set of meters with PTs and CTs, take them through the NRI process, network them together, and program them using a module-based GUI, utilizing engineering mathematics. Easy peasy. Now, coming back to this net zero condition, originally, we would be experiencing full losses out to grid ×2 because of the assumptions made about the other resource, and made worse again because the PV resource was making that assumption about the BESS, and the BESS was making that assumption about the PV. But now we are able to effectively measure that no current is flowing through our calculating meter. Therefore, there shouldn't be any current flowing through the transformer nor the line. Therefore, there should not be any losses at all. The calculating meter communicates no losses back down to the PV and BESS meters, and everyone lives gainfully ever after. With the larger and more complex projects coming to market, peer-to-peer techniques become more and more necessary. Loss apportionment and PPA specificity demands a centralized calculator. Sometimes hardware and design limitations only allow us to position meters at certain locations, and sometimes we're able to use a network of calculating meters to provide a single solution for a complex site. In this example, it would be beneficial to measure the comings and goings at each transformer. It will give us information about the losses at each one. In addition, we can use the topmost calculating meter to measure the actual current going out to POI so that we can have confidence in the line loss. We could then compensate each resource meter based on their real-time usage of the transformer and line segments. As an example, we could have all of these meters communicate to each other so that we have the needed information to complete our calculations. Needless to say, this has been an invaluable component to revenue optimization. It is very satisfying when accurate and honest are also probable. Calculating meters can also be very helpful when we are trying to add a resource to an existing site. Let's say that you have this solar and BESS co-located facility, and it's happily functional. We find that it would be advantageous to add an additional BESS resource to this site. We already have a calculating meter because we understand the benefits it provides. We need only reprogram that calculating meter so that we can tell it to incorporate a new BESS meter. Further, if the latecomer has additional PPA requirements, we can then account for those in the calculating meter as well. I've seen cases where a latecomer was responsible for all new losses, no new losses, or that it must always function as if it has no interaction with the other plants at all. The accountancy for the energy total is the same, but we can assign loss responsibility however we like when we are using a calculating meter. Lately, there have been some projects coming online that are simply too much for a little old calculating meter to handle. Hardware and software limits were being reached. A network of resources like this one can still come online though, with perfect calculations, but we would prefer to use an external calculating device, a non-meter device that is designed for this kind of workload. Some call this a loss compensator, and essentially, it's just a device that is networked to all of the meters that performs calculations in real time, same as a calculating meter would. However, if we use such a device, the calculations are performed by an operator-owned, unlocked intermediary device. Cal ISO has decided that a loss compensator can only be permissible as a scheduling coordinator metered entity project, also known as an SCME project. So now is probably a good time to explain the difference between ISOME and SCME from the perspective of metering. All right, a resource can participate in the CalISO market as one of these types. An ISO metered entity means that the ISO will collect the data from the meters. It also means they will be responsible for the quality of that data. A scheduling coordinator metered entity means that the scheduling coordinator, or SC, will collect that data and submit it to the CalISO, and the resource owner will be responsible for the quality of that data. The choice of how an entity wants to enter the market is up to the owner, but also subject to the requirements of their PPA. But since the responsibility of the data quality is different, the rules for entering the market are different. For an SCME scheme, it's up to the scheduling coordinator and owner to set the metering criteria. Therefore, alternative schemes and calculating devices can be allowed. Otherwise, we can still do standalone and peer-to-peer metering in both types of schemes. Here are some high-level bullets for the differences of getting connected as a metered entity. I'll not read through this, but I will add that for those entering the CalISO market from the Western Energy Imbalance Market, or the WEIM, commonly the process will follow that of an SCME. There are a lot of exceptions and considerations here, but GridSME actually did a webinar on these processes recently. I know that everyone is going to be disappointed that I'm not stepping through the energy market regulatory exceptions and exclusions, but I've been asked to keep my webinar to under 4 hours, so maybe next time. So back to this, a loss compensator can make sense. A site that has a bunch of resources is often going to want something more robust than a meter to do the calculations for the entire site. Further, that data may be useful for our power plant controller to help make decisions. Finally, operating as an SCME will simplify the process with future additions or sell-offs if an owner would like to parse out their site. Recently, I worked on a project bigger than this one, wherein the owner sold off just one of the resources, and the new resource didn't want to be part of the loss compensator. And as it turns out, it was no trouble to remove the meter from the loss compensator. You simply just tell the meter to stop accepting losses from it. Now, since this is a standalone meter, it has to make assumptions about all of the other meters. The resource will now be taking on a larger portion of the losses. However, the loss compensator can still look at the meter. It can see the real amount of losses that it's overpaying on and apply that savings to the rest of the meters. Now, one drawback for those in an SCME is that the CalISO will pull data for free right now in an ISOME scheme. While as in an SCME, a scheduling coordinator may have O&M and risk exposure. Before taking the plunge into an external loss compensator, I would highly recommend meeting with a meter engineer to discuss your options. Somebody like myself can help optimize a peer-to-peer scheme for revenue and help make informed decisions about the size and complexity of a project. Also, you'll get to hang out with me more, which has been proven to help lower blood pressure. So that's nice. To carry on with the concept of a loss compensator, some simpler sites still prefer one to operate. It is true that a loss compensator will have faster calculation times, and it is true that one can help minimize downtimes and help with analytics if coupled with DAS. But consider one more scenario. If we are an SCME, there are not any requirements about calculating meters. Our two resources can now communicate directly to one another. We can execute the simplest form of peer-to-peer metering and still have the detail of the feeder level measurement. Extrapolating that on a little bit, we can now use the same principle to have multiple resources communicating in a daisy chain, updating summed information second by second. So you really wouldn't want to use this for a control scheme because there is somewhat of a communication delay. but the com delay isn't substantial from a revenue perspective, so the data quality is good, just not quite as instant. Again, this is only permissible as an SCME scheme. And that's the last scheme I'm going to talk about today. And yes, there are, of course, more. So we touched on a couple of ideas here that will help clarify our possibilities. With ISO-ME scheme, we must use a calculating meter as an intermediary device between resources if we do want that level of accuracy. And with the SCME scheme, we are free to daisy chain or use a loss compensator. So today, I talked about losses, meter placement, meter methods, and the different ways a resource can participate in the CalISO market. I'll say that most metering 5 years ago was a whole different game. Almost every resource was a single field type, and the integration process was a lot more straightforward. Things have changed considerably with the development of multi-fuel resources and multi-resource sites. And today, we didn't even touch on BESOX metering. I've said it before, but I'll say it again. If your site has some complexity to it, it's worth having a meter engineer take a look. Chances are we can get you optimized. We can help keep your project on track and with the right planning and equipment. Cannot emphasize enough how a bit of consultation can have a large impact. So I kept it under 4 hours, but if there are any questions, they can't stop me from answering them. We can drive this puppy into the night if you guys want. And if you have some specific questions about an upcoming project, we can definitely set up a meeting. And so now we'll open this up to questions. Thank you all.
Yeah, there's some questions in the chat. Josh, feel free to unmute or I can say it. He asked, Casey, do you know which products/vendors actually support the peer-to-peer calculating meter method? We've only come across one.
Yeah, so in the CalISO, the only open source meter at this time are the ION 8650 and the ION 7400. They're completely open source and allow for a lot of logic. SCL 735 is getting close, but it just doesn't have enough logical lines to support larger schemes. And also peer-to-peer is a little more tricky with them. So ION products are the way to go for those CalISO approved meters.
All right, there's another question in the chat from Kelsey. When is the right time to start talking about metering design? I also just found out that the unmute buttons are locked, so I'll go ahead and unmute those if anybody has any more questions.
Okay, I don't think you can be too early to talk about metering design. There's been times where it's been more suitable to move where a feeder is connecting to a bus to change metering than it is to add metering to several points on a bus. So there are scenarios where there has been a scenario where I've run into where I had a choice with a client to either add 4 metering points to their system or to change the shape of how they were connecting to a bus. And so it should start at the design phase if you can. The meeting up design with regulation, metering regulation is can have an impact and save a lot of trouble. Especially with these multi-resource co-located projects or even hybrid projects where you need variable energy component metering. You'll need to measure the specific part of the renewable resource.
Kelsey also said, what about phased projects?
Yeah, for phased projects, again, yeah, that will certainly matter for in the design. especially, you'll want to get metering laid out on a design as early as possible. And as the phases come online, you want your metering structured in such a way that it makes the process, the NRI process with the CalISO as seamless as possible. For that, calculating meters, even phasing in the calculating meters at a particular time can be helpful. So we can help optimize the flow of the project a lot better if we have the full knowledge of all phases that are coming online. If you are thinking about future adds of a BESS to a project, it's better to lay those out as soon as possible, because sometimes the way that you position a meter might not be advantageous for a later add. So if the meter engineer knows that in advance, then we can help make that an easier process for you. Is there a minimum? Oh, a couple just rolled in. Let's see. Is there a minimum size of generator that falls into CalISO metering requirements? Also, what triggers CalISO's requirement for a meter project? We have seen 3 megawatts in a CPV project. I believe the minimum to be to enter the CalISO market is 1 megawatt. Somebody please correct me if I'm wrong. But
I think it's down to a half a megawatt now, Casey.
Oh, half a megawatt. Okay, wow. So if you're entering in the CalISO market, you need a CalISO meter. That's the straightforward answer for that. If you're entering in as an ISO MB, you'll need that. Yep. Sorry, that's kind of a short answer. I don't really have a lot to elaborate on that. High-speed controls and adequate fast metering is critical too. Yes. Are you seeing more and more that we have distinct meters between revenue and controls, and also PMU, transient fast data, NXH, for example? Or are you seeing owners just missing the mark here? How much metering is too much between these needs? Okay, that's a great question. Thank you, Igor. There's a lot of dependencies on what you're driving at here. Entering into an ISO-ME scheme prohibits an external loss compensator, and an external loss compensator is what you're going to need to get high speed, the high speeds that you are looking for. PMU, transient fast data, from meter to meter, the communications are just not fast at this time, but from meter to loss compensator, they can be very, very fast. And so for controls, folks have found it pretty necessary to do so. And what I am seeing more and more lately is that we have one set of meters that is used for revenue in an ISO-ME scheme, and an extra set of meters that does controls. And those control meters have served pretty well for a number of other purposes, such as Appendix H, where you need that real speed. So that, unfortunately, the situation is now with the external loss compensator is that it not being able to participate in an ISO-ME scheme just means that the ISO-ME scheme will function a little bit slower. And by a little bit slower, it's, yeah, you're going to want the separate set of meters. For Gary, is there a resource available that outlines accepted or best practices for calculations and meter placement, such as a white paper or similar document? Interesting. I think that there's a lot of uniqueness for each layout, but I'm not aware of any resources that point to anything like that. And I think part of the reason for that is that there are so many exceptions, and it just, you wouldn't want to be stuck into something like overestimating where a meter is going to be positioned. And I'm not saying that, that from my earlier in the presentation, the best point we can always meter from is the point of interconnection. That means that we are right there at where we are delivering the energy, right? We're not compensating for losses. There's no confusion about what's in front of the meter and how there might be parasitic loads, et cetera. But outside of that, there's not really any documentation I'm super familiar with. Let's see, Josh, please someone learn more about external loss compensators. Okay. Yes. External loss compensators. What devices are available? I know that RTACs definitely do that. I know that there are a lot of devices out there, but it's not really my wheelhouse. Let's see. Trying to think of something else. I know a Nutanix can do that. Sorry, nothing else is coming to mind. What is involved in setting them up, though, is meeting still with a meter engineer to help design the computations that will go into the meter so that we know we're doing it correctly. You're going to have to network all the devices over to that device, the compensator. So it should be capable of either DNP or Modbus or Goose if you're feeling fancy, and getting those calculations back into the meter. So you have to have a two-way street. So you'll need probably like a meter methodology document that describes how those loss apportionment is going to be conducted and how the losses are going to be calculated, and then some extensive testing to follow the different scenarios that might come up. Loss compensators are nice though, because you can really like hone in on those PPA requirements without too much ado about the programming. I will say that programming in a meter is a little bit slower than programming in a known language like C+ or something like that. So it can be a lot easier to get your logical decisions into a loss compensator like that.
Casey, I was just going to chime into Gary's question on the best practices in the white paper. I think the takeaway there is, each interconnection is unique. The physical attributes, the fuel type of the resource, whether you're co-located or not, there's some generic best practices I think we could point to. But in general, I think that each thing has to be treated uniquely because they're all different types of variables that we would have to take into account. So it is really hard to come up with like a true best practice document that captures all of those things. So yeah, this is truly like a custom solution type situation for most projects that we're encountering. For smaller projects where you have a single resource ID, single fuel type, it may be pretty straightforward. And I would point folks to, in the CAISO, the Business Practice Manual for Metering. That gives all of the CAISO requirements as outlined, as well as some best practices around keeping those meters accurate through regular calibration and testing and whatnot. But yeah, in general, you definitely want an expert to look at that and make sure that you're keeping in mind that you've got a resource that has commercial obligations that need to be accounted for, utility obligations that need to be accounted for, regulatory obligations that need to be accounted for, and physical limitations that need to be accounted for. So all those things introduce a lot of complexity. So yeah.
Yeah, thank you. Yeah. All right. I will give it one more minute for any last second questions here. But I think we are coming to a close. I want to thank everybody for coming on. Means a lot to me that everybody showed up today.